Hello, good morning, all.
Good morning, sir. Good morning, Sagar ji. How are
Good
you?
morning, sir. I'm good, sir. I'm good. How about you, sir?
Okay, I welcome on behalf of organizing committee of this FTP. So we'll start within 2 minutes. Let's wait for other to join.
Sure. How do you want to keep the camera? Should I turn it on or should I keep it off during the session?
It's your wish. If you want to make it on, then it's also all right.
Okay, okay. We'll do then. We'll do. Initially, I will keep it active, and as the
I have already
session
made you the
progresses, I will turn
co-host.
it
Uh, I have made you the co-host. You can share your screen.
on. Okay. I hope the screen is visible and voice is also clear.
Yes, sir. It's visible and the voice is clear. But make your presentation in presentation mode. It's in.
Sure.
Okay.
Okay. Will do.
So let's start. And today is a very important session regarding electromagnetic transient simulations, how to perform electromagnetic transient simulations in power systems. And the today's topic is power system simulation with PSCAD and RTDS. So PSCAD is one of the major tools which is used for EMTP simulations. And for this, we have Mr. Sagar Indalkar with us. He is a power system simulation engineer working as a team leader operations at Nayak Power Systems Private Limited. Nayak Power Systems is basically a distributor of this um, PSCAD and RTDS in India. And Sagar received his master's degree in electrical engineering from Sardar Patel College of Engineering in 2019, specializing in power electronics and power systems. At Nayak, he is responsible for consultation, user support, and training on PSCAD and RTDS simulator. Sagar has extensive experience of model development and system studies using PSCAD simulator and hardware in loop testing with RTDS simulator. Sagar has experience in control system design of power plant controller models using PSCAD and RTDS. So on behalf of organizing committee, I welcome him for this presentation, and I hope this presentation will be very useful for you in for all the participants in doing research in power systems. Thank you. And with this, I request Mr. Sagar to start his presentation.
Professor Sanjeev. Thank you so much for the introduction. Glad to be here for this wonderful platform, which will allow us to share the latest happening going on across the world in terms of power system simulation as well as renewable integration. During this 1.5 hour almost, we will share our expertise, our experience working with these tools, and we will guide you on how what is going on and what is the requirement going on across the world in terms of renewable integration modeling and then validation of the power system components in a renewable energy plant to perform something called as the grid code compliance studies and renewable integration studies. So to introduce you to our tool, before I start with this presentation, I will just introduce you to PSCAD. As Professor Sanjay rightly said, PSCAD is a EMT simulator, electromagnetic transient simulator, And what it does is it performs a network solution in time domain. So the software is built such that um, the components uh, they have its own definition, and what it does is it solves differential equation, time domain differential equations in the background, and the outcome of that solution, we call it as network solution, is basically instantaneous values of voltages and current. So PSCAD is a time domain simulator, and it's not a phasor simulator unlike other simulators, and which allows it to capture the network events into greater resolution. So typically, you can also perform a simulation in PSCAD using a nanosecond time steps, and depending on the applications you want to perform. Coming back to our topic of interest, today I would like to discuss about something called as renewable integration, and how it is performed in PSCAD and as well as RTDS. I will introduce you to RTDS later once you know how things have to be performed using PSCAD. Then you can correlate it in terms of hardware in loop simulation using RTDS. Let us understand what renewables are. As you know, uh, considering the world's target to reach net zero emissions, renewables seem to offer a very promising solution because of their excellent uh, energy generation capability, now the low cost, at the same time without any byproduct such as pollution. So, one of the renewable energy projects that is going on a wide scale across the world is solar PV based renewable energy projects, as well as the wind turbine based projects. So when I say renewable integration, it includes both wind as well as solar energy generation, and along with that, considering the intermittent nature of availability of power when it comes to renewable energy, nowadays there is also a trend to have battery energy storage system along with the solar or wind energy plant to take advantage of energy generation and utilization gap. So the discussion which we are going to conduct today will be applicable for all solar, wind as well as battery energy storage systems. Uh, so uh, so a renewable energy plant is basically it has a source. And that source, let's say I'm discussing about solar. That source is solar PV arrays, which generates DC power at certain voltage level. And as you know, we cannot utilize DC directly. Our grid is and predominantly it is an AC grid. So we require some power conversion devices, basically your power electronics converters that will convert this DC to AC. And then there comes a converter in between, which will generally convert DC to AC. Then we will require some other component we will discuss in the upcoming slides. And ultimately, this thing should be connected to the grid. So now we have power electronics into the picture, and to so we require very advanced control. For example, an inverter control that will take certain decisions of what to inject, at what frequency to inject, at what voltage to inject. So you require inverter controller along with it, and you require something called as a plant controller along with it. So renewable energy, especially converter-based renewable energy systems, are very notorious because they are unlike traditional synchronous machine-based systems. They do
Sir,
not offer inertia to the grid.
sir, your slide
These
is not
systems,
moving, I think.
yeah, I'm not. I'm just starting up the presentation. I'm
Okay,
not
okay,
to the
okay,
next
okay,
page yet.
okay, okay.
Yes, yes. As I said, renewable energy is because of the very nature of it, is not very friendly with the traditional grid that we have been using till date. Why? Because it doesn't offer inertia to the grid during a fault or disturbance. It does not contribute to fault current. Why? Because converters are current control devices. So the rated current and the fault contribution by a converter is almost equal to the rated current of the converter. You can consider 30%, 50% extra to supply fault. But then again, it is not as good as what used to be present for a synchronous machine. So now you have two problems. There is no grid inertia from these renewable energy sources, and they do not contribute to fault current. And there comes the third problem. That problem is the dynamics. So every converter will have its control, and when you have controls, manufacturer specific controls, their behavior will be very different. So a converter or a plant from certain developer, let's say a plant, will have very different dynamic behavior compared to a different plant of different rating and different make. It's very difficult to predict how these things will behave in a real world scenarios. And ultimately, what our aim is to maintain grid stability. So, as expected, the regulatory bodies across the world, including India, they have laid certain regulations for these renewable energy projects, and they have to comply to that regulations so that their plant can be connected to the grid and they can start billing to the end users. So that regulations, these are called as grid code compliance, called as grid code. So the grid code specifies how a plant should behave during normal condition and during disturbance. Now, as I said, every plant will have a different behavior, a different dynamic behavior. And how can we know what behavior is to be expected from a particular renewable energy plant? Uh, it is not known unless we perform certain studies, right? So these studies are performed in RMS domain as well as EMT domain as well. And the tool which is preferred to perform these studies is called as PSCAT. It's a EMT simulator. You can model controls in it. You can model power electronics, switching based power electronics into it. It can capture harmonics, all level of details considering a renewable energy plant. And that's the reason there is a need to perform renewable integration studies into PSCAT to confirm that your plant that you are installing is complies to the Indian grid code or whatever country it is being installed in. So now comes the topic renewable integration, modeling and details. Now we know why is to be performed. Now let us see how is to be performed. So when I say a renewable energy plant, um, let's consider a solar energy example. Here is the overall schematic of the plant. Now, as I said, a renewable energy plant will have thousands of components, right? It's not possible to model and not required to model all those components. What we have to do is we have to model the dynamic behavior of the plant. Everything which is required to model the dynamic behavior of the plant. So let us understand what those components are. Now, typically, a solar energy plant will have your PV panels. In this slide, what you see is just two panels, but in reality, there will be hundreds and hundreds of panels on a typical solar energy plant. So, so here you have hundreds of panels, and then you have your converter, okay, also called as your inverter because it converts DC to AC, and this inverter takes care of your maximum power point tracking uh, functions. So it converts DC into AC, and because it has switching based power electronics, your IGBT, so it will have non-linear components in out, and those we call it as harmonics, right? Interharmonics, characteristics harmonics will be present in the output of the converter. So we will require certain filters that will filter out and give us a near sine wave And then now the converter typically operates at uh, around 0.69 kVs at low voltage interface. Whereas the grid is as a at hundreds of kVs of voltage, for example, 132 kV, uh, 400 kVs. So we require something called as an inverter transformer connected to a bank of inverters that will elevate that voltage from 0.69 kV to, let's say, 33 kV. Now, once this voltage is elevated to 33 kV, step up to 33 kV, as I said, there's not a single panel or two panels, there are hundreds of panels. So we require something called as a collector system. It's called as cable collector system, which can have hundreds of cables collecting power from all these independent converters and clubbing it together, collecting it into one place. And that place will be this. So you may have hundreds of cables and then all bringing it back to one location. Of course, this cable will have its own reactance, reactive power absorption, reactive power absorption. But the voltage here is still 33 kV, not up to what the grid is requiring. So you have something called the main power transformer or your transformer, which elevates this voltage, step ups it from 33 kV to your POI voltage. The point of interconnection, POI, is the place where your entire plant output will be connected. It's the location at the of the grid where the entire output of the plant is generated. So, so these terms are very important because when we go ahead, I'm going to use these terms quite a lot. Okay. Now, if you notice, um, now this type of model is called as a simple machine infinite bus type system. Why? Because uh, if I try to model everything, uh, it becomes very difficult to model hundreds and hundreds of inverters. So we club it together, we aggregate the entire plant into a single energy generation source, which is what the grid utilities wants. They want a simple representation of the entire plant as one energy generating source. So we have to aggregate all this into a single generating source so that the behavior of the plant can be studied. Okay. So if you notice here, the converter has a convert. There are a number of converters. They have their own inverter controllers. So there should be one more controller that is controlling the entire power output of the plant or the entire behavior of the plant. And that task is done by this component called as PPC or power plant controller. Okay. Power plant controller. So this PPC is like a supervisory control. It looks the operator sits at a location where the PPC is remotely accessible, and he asks the plant to generate certain active and reactive power, right? So this PPC requires set points from the plant operator, and it requires measurement, and that measurement will come from the regulated bus. In our case, it will be your point of interconnection, POI. So PPC will take measurements from POI, and it will ask for set points, that is the operating point of the plant, from the operator. And based on this inputs, it will take certain decision. Now that decision is basically P and Q order, active and reactive power order from the PPC. And that will obviously go to your inverter controller. So the inverter controller will input P and Q order from your PPC, and it will correspondingly generate individual outputs from the converter. That will generate, there will be certain losses, and ultimately the power will reach at POI, it will be measured, and this forms a loop. It forms a closed loop. Now, this is how a typical uh, a renewable energy plant functions. So from this point, what we learned is, if I want to look at the dynamic behavior of the plant, it is very important to study the response of the PPC, right? It's very important to study the behavior or response of the PPC. So I need to model this PPC in great detail, right? And then the control function inside the PPC will be manufacturer specific, right? Every manufacturer will have its own control philosophy of how to do things, and so we will have to model the entire PPC, whatever it is executed inside the physical controller. The same model is to be implemented into our simulation. Next important part comes your inverter. Again, inverter is the dynamic device, and it follows the PPC. Whatever PPC asks, it does. Along with that, inverter also performs certain additional functions. So again, it becomes important to model this inverter controller great detail. So let us see how these things are modeled. So overall plant will consist of your PV panel, your DC converter. This is basically your boost converter to obtain maximum power point tracking. Then you have your DC to AC converter. Then along with this converter, you will have your controller that will control the output of the inverter. You'll have those filters, harmonic filters. Then you'll have your inverter transformer. This one inverter transformer. Then you have your collector system. You'll have your main transformer or grid transformer, and then you will have your point of interconnection. Okay. And ultimately, all these things will be controlled by one supervisory device. It is called as a power plant controller (PPC). Okay. Now, PSCAD has the capability to model all these components in very much detail. For example, you can model PV plant in PSCAD, enter the number of modules in series, parallel, output of every cell, the behavior of that can be modeled readily using the library components into PSCAD, that's called as the PV panel, and it will generate certain power output, DC output. Okay. Apart from that, what you have is something called as a collector system. So the collector system, this is the actual SLD of a collector system. You'll see a number of converters located here, right? And then there you'll see a number of cables connecting all those converter units together, and then ultimately reaching one point. It will be over here. Okay. So the collector system uh, collects all the output from the inverter, clubs it together into one single cable, and then we connected it to your uh, main transformer, right? But again, we are not going to model n number of inverters because it's very difficult to perform uh, modeling hundreds of simulate inverters into a simulation. Why? Because converters are switching based devices. They operate it at very high switching frequencies. So to model or capture those switching frequency, it forces us to use a very small time step, a very small sampling rate, small time step, so that the behavior or the actual switching is captured. So typically, if you use hundreds of inverters into the plant, um, then the simulation will take very large amount of time to run without adding any actual benefit to the overall plant. So what we do is we aggregate all the inverters into one, and then we we aggregate all the inverter into one, and then we aggregate this collector system into a single cable, and then we represent it in this fashion as a single cable with the impedances. Okay. So uh, now now we are working on aggregating things together, clubbing it into one single behavior. So as I said, multiple inverters will require heavy calculation burden. So instead of modeling hundreds of inverters, I will model one inverter with one inverter controller, and then I will use something called as a scaling component. Okay. So this box which you see is a current scaling component, and depending on the number of converters, I will I will put this input as, let's say there are 32 converters. I will put 32 as an input to this, and it will multiply the power output of each inverter two times. So this component is readily available within the PSCAD library. It's called as current scaling component. And again, the cable. Now, since the inverters are clubbed and aggregated, cable is also aggregated into an equivalent cable. So, uh, so the rest of the system, again, it will have certain filters, inverter transformer, everything will be clubbed as one of each of the component with the aggregated impedances of those components. And your simplified plant diagram or SLD will look something like this. Okay. So we'll look at from the right. So you have your PV inverter. Okay. This is your photovoltaic uh, converter. Then you have your inverter transformer. This is the aggregated diagram. Then this is the collector system equivalent, aggregated cable. Then you have your filters. Then you have your main transformer. Then you have your transmission line. This is your POC, point of coupling. This is your point of interconnection. This is your interconnection transmission line. And then you have your grid. Okay. Then you have your rest of the network grid. So this is how the plant will look like when you model it actually in the simulation. Now, other components of a plant are your inverter controller. As I said, it will follow P and Q command from the power plant controller, the plant controller, right? And along with along with generating P and Q, it also perform other aspects. For example, the DC bus voltage control. Right? It also performs DC bus voltage control. It also performs frequency response. I will come back to that point again. And it also provides LVRT, HVRT support. Now, as I said, PPC is a supervisory control, right? And typically, uh, the rate at which PPC takes a decision is in the range of milliseconds. So, for example, the fastest PPC available, which I have seen, is operates at a sampling rate of 5 milliseconds. Okay. And the overall response time comes nearly 100 milliseconds, considering all delays and downstream devices. So, so the PPC basically is a slow controller which can take decisions in the range of 50 milliseconds to 100 milliseconds. Uh, but but that's a problem because LVRT, low voltage right through, high voltage right through, these are very short-lived event. They can be they can last for a very small time. For example, a half cycle, quarter cycle, one cycle. These will be very small events, and and for half cycle, the PPC may not have time to respond to this event, right? So so for providing LVRT, HVRT support, the responsibility has to be given to someone which is very fast, and that fast device is basically your inverter control. Now, why inverter control is faster is because it is actually connected to the power supply. The inverter controller is actually part of your power supply. For example, if you go back here, you see PPC is receiving measurements from the grid, right? It's receiving measurements from the grid. This is a digital measurement, and then it is giving order. So if you see this portion, this is like a communication, digital communication based device. It does not have any power circuit, right? Whereas an inverter, it is actually generating that power. It is close to the power circuit, so it is able to take decision very fast compared to that of power plant controller. The responsibility for responding to LVRT, HVRT events are kept with your inverter controller because these are fast devices. So, your inverter controller, I will not discuss this into much detail. You already have studied inverter controller. You know what APC to DQ transformation is, right? Reference frame theory is. Then we just brief it to you. The inverter controller will basically ask you for a reference for whatever P and Q is to be generated. It will measure that P and Q here will take out error, it will pass through a PI controller, and then will perform parse transformation. Ultimately, it will give us the direct axis and quadrature axis current components, ID and IDQ, for ID and IQ. And then you have your inner loop where the actual measurement is to be taken from the inverter, again converted from ABC to DQ reference frame, and then you get your IDIF. You take the error, you pass it to a PI controller, and then ultimately what it generates is VD and VQ. Right? This is basically a decoupled, decoupled control, because you now have you are now able to control active power and reactive power independently. Right? So to do this all this activity, we require this inverter control. So ultimately, what we want to achieve is ID and IQ. So now you are in DC reference frame. Now you are in DC reference frame. So you can change the voltage to obtain the desired ID and IQ. And ultimately, VD and VQ, these components will be brought back to uh, your ABC reference frame, which will give you AB, VV, VA, VB, VC, which can be used as a modulation wave to the PWM circuit. So, um, so your inverter will have outer loop, which will follow P and Q command. It will try to reduce that error between set points and uh, measurements. Your inverter control will generate references, voltage references will be to obtain that ID and ID. Okay. And then ultimately that references VAVBVC will be given to a PWM circuit like this. It will generate a pulse with modulated uh, waveforms, ultimately resulting into uh, your AC side voltage. So the converter typically has certain losses. For the switching based converters, you require filters, and these are very high switching frequency devices these days. Okay. So they require very high resolution based modeling, okay, which is possible in PSCAD. Along with this, you also require something called as the PLL, phase lock loop. Now, if you notice all this setup, I'm over looking at the grid voltage, right? So the inverter will require one more input, and that input is theta. That will come from the grid, the voltage of the grid. So the PLL basically tracks the voltage angle of the grid, and according to theta, you use this theta into the path transformation matrix, and then based on this theta, the inverter will generate certain voltage. Now this looks for theta because it's a grid following converter. Now there are grid forming converters as well, which doesn't require this theta. This one is grid following. Now comes your power plant controller PPC. The main task of a PPC is to perform active power and reactive power control, okay, at your POC or POI. So active power control is your P control, and inside active power control, it has to perform one more function that is called as uh, frequency response. It's called as frequency response because the grid code asks the developers, the renewable energy developers, that their plant should provide grid support during system disturbances. For example, change in frequency. So if the frequency deviates from your rated frequency, 50 hertz, with certain deadline, the plant should take some action. And typically, that action is the frequency goes above 50.05. It should reduce active power. Why? Because active power related to frequency, and if the voltage or if the frequency goes below 50 hertz or 49.90 hertz, To be specific, as per Indian grid code, the plant has to inject additional real power into the grid to support the grid. So that is what has your frequency droop control. So these two things become part of your PPC. Apart from that, it has to also supply reactive powers. It has to provide reactive power support. Now, based on the requirements, typically the voltage requirements, a PPC has voltage control, voltage droop control, reactive power control, and power factor control, so that it can operate at certain operator inputs. For example, at certain to deliver to generate certain to inject Q to obtain certain voltage. Okay. Then there is power factor control as well, where you can ask the PPC to operate the plant at let's say 0.99 power factor. Correspondingly, it will generate more Q so that that power factor is attained. Already discussed frequency response. Apart from that, you also have something called as um, anti-wind-up during LVRT, HVRT event. Now, if uh, as I said, LVRT, HVRT is not the responsibility of the PPC, but rather than the converter because it is faster, a fast behaving device. But the PPC should take some decision, right? Either to supply additional reactive power support during LVRT event to seal the fault, or it should freeze. Typically, take one of the two decisions. Most of the PPC they freeze the P and Q order during LVRT and HVRT event. The reason is simple. LVRT, HVRT are a very transient event, so they change very quickly. And but the PPC is a slow device, so uh, we find it very difficult to respond to fast changing uh, voltages. So it typically takes a decision to not to respond to transient. That decision is basically to freeze P and Q output to whatever it was before that event. Okay. So the PPC freezer, it will let the inverter take control to uh, to keep the plant running, operating, even during a low voltage or a high voltage right through event. The PPC, it basically has a control loops, active power and reactive power control loops that will basically generates your P and Q order. It's very interesting to discuss about design of PPCs, but that may be a separate topic of discussion. To explain to you briefly, a PPC basically takes set points. Let's say this is your uh, active power reference. It takes measurements. It passes the measurement through a filter. Then it takes out error. That error is passed through a PI controller. And PI controller basically takes action so that the error is minimized. And correspondingly, it will generate certain P order, okay, which will go to the converter. Similarly, the same philosophy will be used for Q control as well, reactive power control. Along with that, it has to perform other functions. For example, the frequency loop function, the grid support function. So you have your frequency loop here that will inject active power or reduce active power if the frequency is above or below or above the that band specified by the grid code. Similar function it has to do for voltage controllers. Okay. There are many other controls that are typically part of PPC. But as I said, it's very extensive discussion, and we require a separate another day to have more discussions on this itself. Okay. Now, um, now, so a PPC, also called as a park controller, also takes performs active and reactive power control at your regulated bus. That is PUC. It's a closed loop control and it has very slow response. So typically in the range of now this is a slightly older data. Now PPCs have become faster. So I have seen response times in terms of 50 to 100 milliseconds. Okay. Then you have your inverter control, which follows the PPC and operates during NVRT, HVRT. It takes a decision, and it's a very fast controller because it is part of the power circuit. Okay. Now, once you model all these things, which all things? These things. Once you model all these things, you model grid, you model your transmission line, you model your transformers, collector system, filters, any reactive power compensation devices, your inverter and your converters and your DPC. Once you put all these things together, you have to perform a study. Okay, put together and you perform a study, and that study typically involves certain tests. Okay, to check whether to check whether uh, your plant follows the grid code or not. Okay, and typically that test involves set point changes. For example, you will put the PPC into active power control mode, and you will give the PPC certain set points. Now, typically that set point is performed at every 10% of the operating range. So between 0 to 100% P, uh, will give a set point to the PPC. Let's say uh, 0 active power, then 10% active power, 20% active power, 30% active power. Will go all the way up to the entire range, operating range of the active power control. We'll give it as a set point to the PPC, and then you will see whether that set point is achieved or not by the overall plan. So you see here, it's not the blue is your active power command given by the PPC for a set point of 1 per unit. These are per 1 per unit, and then you have your PPV, which is your measurement, your active power measurement, and you'll see that this closely follows, right? This closely follows this closely follows your command, right, and your set point. So, and then you have to check whether the rate at which this power changes matches with what the grid code asks you to do, and then take out the results, report it into nicely into a document to confirm that the plant meets the requirements. Now, um, now that forms your active power step changes. Similarly, you have your reactive power test, where you will give certain reactive power set points to the PPC, and then you will check whether that responses are met or not. In this case, you can see that it matches. It ultimately achieves that set point which is provided, but it may not do so depending on the control philosophy or any parametric changes, the PI controller values, the dead band, the ramp rate control. So, especially this is important since your inverter will be manufactured by someone else, your PPC will be manufactured by someone else, and then the plant is operated by someone else. So, all these things should work together to achieve the desired output. Similarly, you have your voltage reference test. Now, typically, when we say voltage reference test, uh, the grid code requirements in India doesn't require you to have voltage control as such, but it requires you to have voltage droop control. So when I say droop control, what does it mean is disturbance control. So whenever the grid voltage deviates from the rated voltage and a certain set point, the the PPC should inject certain Q or reduce certain Q so that that voltage is maintained at VOI. So we don't have voltage reference, we have voltage tube reference for Indian requirement. But nonetheless, the PPC can still have voltage reference control mode already in the features. Then you have your frequency reference test. So in frequency reference test, what you do is you enable the frequency troop settings of the PPC, and then you create disturbance in the grid. So you reduce or increase the grid frequency. So let's say 50, you will go to 50.5, or you go to 49.8, and then you will check whether the PPC is ordering, and for the plant, overall plant is ordering uh, grid support or not. So let's say if the frequency falls below 50, then you should inject active power. If the frequency goes above 50, then you should reduce active power. So that forms your frequency. Along with that, uh, you also have certain other tests. For example, LVRT, HVRT test, where you create a fault at POI. So to check whether the plant stays connected during a LVRT or HVRT event. Now, apart from this, there are many other tests specific to Indian Grid Code, such as amperage control, uh, to check whether the plant remains can supply active power even if the frequency is 52 hertz. So those things has to be those setups. Uh, the scenarios has to be set up into the PSCAT model and performed so that the plant response can be verified. Then there is one more test called a harmonic test. So as you know, renewable energy, these are power electronic based devices, solar, wind, BESS, with all our power electronic based devices. So they generate harmonics, right? So they always have certain harmonic components into it. And as the as the renewable penetration increases, the harmonics will also increase. So the plant has to take care that the harmonics injected by the plant are uh, within the limits uh, specified by Indian Grid Code. Okay. So typically, Indian Grid Code, the limits which we use is specified in IEEE 519 standard. So to do this test, for performing harmonic test, you will measure the harmonic profile of the inverter. Then the same harmonic profile will model it into PSCAT as current injection. So if there are 100 converters, you'll model 100 current injection, and then you'll model the plant devices, the cables, transformers, and ultimately you will measure the harmonic distortions at the POI, and we'll check whether the distortions are within the safe limit. If they're violating, then again uh, you'll have to deploy certain mitigation devices. These are basically passive filters. So if you have fifth harmonic problem, you'll install a fifth harmonic filter, and after filter, you'll check whether uh, the harmonics are within the IEEE 500 standard. So this is the overall uh, idea or process of performing a renewable energy modeling as well as test in PSI. We'll see a actual case which I have created in PSCAT. I hope you're all following me till the. So this is a typical renewable energy plant example. Now this is a very simplified one. Okay, a real plant will have much more components than what I have in the on this case. But I have kept it very simple so that it is easy to understand. If I correlate it with the SLD which I showed you in the past, you see, if I this is something called as a page model in PSCAT. This is your PSCAT version 5. This is your canvas, and this is your workspace where I have loaded all the cases, okay, with project files. So, so this box. this box that which says solar farm is actually a page, sub-page, which includes your uh, all converter component. So those are your PV array, the solar PV array. It will take your radiation temperature references. Then you have your converter, your switching base, your IGBT base converter, and on the right you have your filters. Right? These are your filters. Then you have your inverter transformer. This is your inverter transformer, and then this box is your current scaling component. This box is the current scaling component, where I am specifying a scaling factor. Now this number this appears as a label to you because um, these are provided through this edit parameter enter. So the number of inverters specified is as 50. So 50 into each inverter, that is 50 into 2.75. That number will form as a single inverter. Okay. So you have your scaling component here. Now this component is a older version of that component. Newer version is available in the library, ASCAD library. It looks something like this now. This one. This one is your current scaling component, okay, the newer component. Again, it will ask you for a scaling factor. Okay. Just like how what we did in the last exercise. Okay. So this is your converter. If you see these wires here, UP, PU, these are the references to the converter. And where are they coming from? They're coming from your PPC. Okay. So this block is your PPC. And on the left hand side, what you see are the references. Okay. This voltage reference. So typically, PPC performs five functions: active power control, reactive power control, voltage control, frequency control, and power factor control. So this PPC performs only four control. It doesn't have frequency control function. Uh, the one which I have in front of me. So it requires four references: voltage reference, active power reference, reactive power reference, power factor reference. And these references, uh, it is, these are the set points which the plant should operate at. And on the right, what you have are the measurements. So V, RMS, POI, this is the voltage at the POI, it's active power at the POI, it's reactive power at POI. So based on the measurements and set points, the PPC will take certain decision. If I go inside this box, you'll see a typical PPC. It's a very crude form of PPC, very simple PPC. It does not have any modern function. This can only perform active power, reactive power control, voltage control. It doesn't have frequency support, rampant limiter. It doesn't have any other important function that a typical PPC requires. But um, this does the work to demonstrate how the controls inside the PPC looks like. It's much more involved control than what we have here. So, so if I right click on this edit parameter interface, I have to specify the plant ratings. I have to specify the values of the PI controller, gains of the PI controller, limits, E limit, Q limit, operating limits of the plant, the LVRT, HVRT threshold below which the PPC should freeze or supply reactive power, or above the threshold above which the PPC should supply, reduce the provide reactive power support. All these are specified inside the parameter interface. Okay. On the right, typically what you have is a collector system. I have not modeled it here. Otherwise, there could have been a cable model here present with the aggregated cable plant. And then your main power transformer would have been here. This is 33 kV plus. This would have been here, and then this would have been at, let's say, 110 kV. This is a very simplified example just for demonstration purpose. Okay. So, so the number of tests which I discussed in the slide, these are again performed here. So what you have here is each step. Okay. So in each step, you use this control logic. So you're giving time reference and you're asking you are given a time reference to a comparator. When the time crosses uh, 10 seconds, it will generate it will change output 0.2 from 0. So at 10 seconds, my P set point to the PPC will reduce from 0.9 to 0.2. Similarly, there are other ways to do this. This is not one way. There are others. There's what we call as sequences, which we can use to generate those time varying set points. And then this is a gain function. It is basically scaling the power output on the fan. So the if you see this set point is required in megawatts, and here I'm providing it in per. That to multiply it by 100 so that set point reaches the active power. So on the right, if I just move up, you see this is my VRMS V1, the RMS voltage at VY, which you see is more or less stable. Okay? It's more or less stable, constant. At the bottom, what you have is your PPOC. What is PPOC? PPOC is the active power measured at POI. Okay? The one in blue is your active power measured at POI. One in green is your reactive power measured at POI. Okay. So if you remember, the set point which we kept is initially for first 10 seconds, my active power set point was 90 megawatt or 0.9 per unit, which changed to 0.2 per unit at t equal to 10 seconds. So that set point changed, and so is my active power at POI changed from 90 to 0. Similarly, we did not make any changes to reactive power, but there is a small dip in the reactive power because of injecting additional active power. There was minor change in the voltage at the POI. And because of that, you'll see a small change in Q as well. Okay. So similarly, this is your PPC command order from the PPC, which will go to the inverter. Okay. This blue is active power command, green is reactive power command, and then you have to correlate whether the inverter is correctly following it or not, okay? And whether there is instability or other uh, compliance issues with the response of this model. So just like how you did your active power step, you have to do reactive power step also, where you will change the reactive power set point. So here I'm changing voltage set point. Okay, this one is for a voltage set point. And the voltage will change at 10 seconds from 1 per unit to 1.05 per unit. The voltage changes, and so is my RMS voltage. It increased from 1 per unit to 1.05 per unit. And to increase this voltage, what does the inverter do? It will inject reactive power, right? So it will inject more reactive power so that this voltage is achieved. So if we want to reduce the voltage, it will absorb the reactive power. So, and these are your PC commands. So blue is more or less constant, but Q has increased because voltage set point was increased. Okay. Similarly, you have to perform reactive power set point changes, right? And power factor set point changes and see whether the response has been correctly followed up. At the end, what you have to perform is the fault rate to release. We will apply a deep fault at PUC. Typically, these are performed at 85% voltage, 50% voltage, 0.15% voltage, and then you specify the duration of that fault. For example, 0.43. These by like 400 and 0.43 seconds of fault, and then what we have to check is whether the plant remains connected to the grid even during this LVRT event, and it comes back to normal or stable after the event goes away. So VRMS POI reduced to almost zero at t equal to 10 seconds. And so my active power reduced, my reactive power also is reduced to zero. The voltage fell to very instantaneous volt here. See, this is the instantaneous voltage. Okay. Now this here you can see clearly see the harmonics, right? This is not pure sine. If I perform a Fourier transform, fast Fourier transform of this form, I get to see the harmonic contents into it individually. This is possible in PSCAD. So there is between the voltage uh, and then the inverter kind of was able to withstand that event. And when the fault went off, my plant started operating at the plus and minus set points. If you see the voltage returned back to normal, so my and so is my P and active power and reactive power generation. So the plant power is touched, the fault right through, and uh, this the aim of the study was achieved. Um, is everything clear till here? Okay. So now that's about how things are performed in PSCAD. Now here the question arises. One question arises here, and that question is now your entire study is dependent on how good the model you have built, right? So how accurately represents the actual controllers, the actual plant. So it is possible that due to unintentional causes, the model may not be an actual representation of the physical controllers devices on the field. So to avoid that problem, we have to perform validation of the plant devices. And one of the most important validation is validation of power plant controller model, PPC model, which you have written on built in PSCAD. So that model must be validated before you can say that okay, this is the actual representation of the physical controller, right? So this can be performed using RTDs. So RTDs is basically RTDs is formed for real-time digital simulator. It is also a EMT simulator which can perform time domain simulation in real time. When I say real time, what does it mean is if I ask the simulator to generate an output every, let's say, uh, 50 microseconds, will generate those output at exact 50 miles. So the benefit of doing that is you can connect external physical devices with the simulation uh, as if uh, these are considered one system. So in RTDS, uh, you basically have uh, uh, a very powerful processor, a computer, which looks like this. This is called an RTDS Nova Core. It has chassis and processor both on it, and along with that, it requires input-output cards. Okay, that can be interfaced with external devices. For example, relays, converter controls, with PPC, or any such devices which is under. So, the build, everything which
No,
you see here
please put
is
it
that.
in presentation mode. Please put it in
Oh, sorry.
presentation.
Oh, sorry. Is it visible now? Okay.
No, no, it's still in the notes mode, not presentation.
It says, okay, okay, I got it. You wanted it to be like this.
Yeah, now it's visible.
Okay, okay. Thank you, thank you. So, yeah, okay. So, the setup will have a simulator or a simulator and input output cards and your device and test. There can be n number of devices that can be tested through this method. Typically, it will be popular to test like HVDC replica controls using RTDS simulator. Similarly, you can test converters, controls, inverter controls, relays, uh, perform cybersecurity type applications using the HIL setup. So the plant which we modeled in PSCAD like this. Now we'll model it in RTDS. It's called as RSCAD. The software is called as RSCAD. The plant is modeled here, and then the device under test will be a physical device. In our case, it will be either a motor controller or it will either be a PPC. The PPC will be a real PPC, and then your model of the plant will be a simulated one. So inverter is simulated, grid is simulated, transformer everything is simulated. Only PPC is a physical controller. So what we'll do here is we will create this model. You will interface the physical PPC with the simulated grid, and you will perform the same test which you performed on the PSCAD model. You perform the same test which you performed on PSCAD model, and you will compare the response, whether the responses are similar or not, same or not. And if the responses are different, it means the model which you created in PSCAD may not be the correct representation of the actual device. Okay. So, so RSCAD has this interface called a runtime interface where you can see the output, change parameters, change control inputs. Okay. Now, typical validation will involve uh, overlaying responses obtained from VSCAD and responses obtained from RTDS simulator, and you will overlap them and see whether these responses matches each other. Okay. If the model is well built, then the response will match very accurately. But there will be differences. There will always be some differences uh, because you are using a physical device which has something called as communication unit. If you are using communication protocol, so it will have certain delays into it, which is not part of a PSCAD simulation. So you have to measure that delay with the RTDS setup and model that exact same delay into PSCAD using the delay component. Once you know the delay, you model it, and then the responses can be compared. So if you see here, the responses are a near match, right? But once we add delays, you see minor mismatches starts to appear. Okay. This is the set point. These are the measurements. Minor mismatches started to appear, which is okay. Another thing which we'll notice here is PS kind of instantaneous value simulation, whereas RTDS is also EMD simulator, instantaneous value simulator. But the device is the physical device, which is using a communication protocol. And that communication protocol is called as Modbus. That communication protocol called as Modbus protocol. And it's a slower protocol. Typically operates in the range of 5 milliseconds to 1000 milliseconds. So here, all the things are not updated instantaneously. We see such a ramps like a staircase in the output of the PPC and the input of the PPC because it's using a communication protocol. So values are not updated instantaneously, but they have a delay, and so it appears like a step. To match the two responses, the PSCAD model should also be made capable to to model this Modbus delay. Okay. To discretize the control and add the Modbus delay so that the model developed into PSCAD is becomes a more uh, real world representation of the system. Right? Then you perform all the test, and then we'll see whether the responses matches each other or not. They may not match due to delays or certain time constants or differences, physical differences between the model and the devices. Okay. We have performed this validation of PPC for multiple OEMs. We'll just briefly discuss that experience. So typically, you require RTDS simulator to do that. Along with that, you require a communication card, which is called as a GTNet card, where we can install Modbus protocol. It's a TCP/IP based Ethernet based protocol, and then you basically what you do is you are setting up a you need to know what are the input output of the PPC measurement settings, and then you also need to know the Modbus map, physical PPC. Modbus map meaning address where where the set point should go and where it should come from. Right? So the addresses should be mapped. What is Modbus mapping? The PPC. That we do using what we call as a Modbus editor. We specify all the set points, measurements, commands, and these can be done through one of the four methods. So Modbus is a 16-bit integer only, so it cannot support real numbers, it can only support integers. So we have to do some conversion, scaling conversion, so that decimals can be accommodated uh, in this what to call. So typically we scale it so that all decimals are becomes integers, and then internally in the controller or integers we can scale it down to the desired level. When this is taken care of, when Modbus mapping is performed, we'll send a command to the device and we'll read the output of it. And through this method, we'll measure the delay. Typically, what we saw is the delay is between 90 to 100 milliseconds. And dependent on the polling rate of the PPC, the devices which are in between the PPC and the other device, and the receiving devices, that will be measured and then modern thread listed, and then we'll compare the two things together. Okay. And this way, uh, we can generate a report, and we can confirm that the model developed in PSCAD is a true representation of what you have in the physical controller. But these same operations can be performed for inverter as well, or the entire plant as well, consisting of many more dynamic devices. So that's all the conclusion of this discussion is. If you have any questions, you can let me know.
So any questions from the participants? Sir, I request please just repeat the distinction between RTDS and PSCAD once again. How RTDS is useful for testing real-time models?
So that's a good question.
Yeah, this slide.
Now, I will relate it to PSCAD so that you will know. So theoretically, PSCAD and RTDS are same because the solution engine is same. Um, PSCAD is also EMT simulator. RTDS is also an EMT simulator. In fact, PSCAD and RTDS came from one location, that is your Manitoba HVDC Research Center is the home for both PSCAD and RTDS. RTDS was sold as a separate company later on to Amitech. So both have the same mother, both with the same method of solving network solution. The difference is how fast they solve the network solution. So PSCAD is a offline simulator. Offline simulator meaning work it runs on your computer, your general purpose computer, your laptop. And depending on the complexity of the network, it may take, let's say, a 10-second simulation will take couple of seconds, or it may take couple of hours, depending on how complex the model you have built, how much components you have in the model. So it will take longer or shorter. Okay. But a real-time simulator is such that no matter how complex or uh, simple network you build, it will solve it exactly at the same rate at which your wall clock operates. That is your real time. So let's say you are performing a 10 microsecond simulation, and you want to receive output at every 1 microsecond. The output of RTDS will be exactly delivered at every 1 microsecond, and that will exactly match your real world clock. So that benefit gives you an advantage to interface external devices. That external devices, let's say it's a relay, for example. So you're testing a relay. Okay, so the relay will receive the the plant will be, or say the test bed will be modeled inside, or the grid, the network will be modeled inside inside the simulation, inside RTDs. And then the output, basically the relay is a physical device. So it requires physical input or so typically a relay requires three voltages, three currents. Right? VA, VB, VC, IVS. So those input outputs, voltage and current, we will take it out from the simulator through this card. It's called a digital to analog converter, and that will give you your voltage and currents. If the relay requires voltage or current at certain power level, then for amplitude, then this we can have an amplifier in between that will amplify that voltage and current to the voltage that matches the relay's requirement, and then that will go to your relay. So the relay will look at the grid condition. You can create scenarios or events inside the simulation because it's a simulation. You can create whatever fault you like or whatever disturbance you like, and the relay will look at those measurements and it will take a decision as if it is talking to a real world grid. Right? And then it will take a decision. That decision will be relayed back into the simulation. So let's say the relay is taking a decision of trip the breaker. Then it will trip the breaker inside in the simulation model. And then you will not only be able to test the performance of the relay, whether it took the right decision or not, you will also be able to check whether that decision deteriorate the network condition or not. For example, you opened up the breaker and that leads to system imbalance, right? That can also be checked. And then you can also check whether the relay was able to withstand that disturbance, that voltage or system imbalance. Okay. So this is like a closed loop testing of um, closed loop testing of a physical device in a simulator. And to do that, RTDS requires a dedicated hardware. That hardware is basically a very powerful processor, which is housed inside this chassis. Okay. So this is called a Nova core. It has a IBM processor, which can solve all this network in real time. I hope this gives you an idea of how RTDS and ESCAT differs.
Yeah, thank you, sir. Thank you. So, any participants' questions? And I also request Mr. Sagar to please give us this presentation so that we can upload it on ATAL website. Please send it us through an email.
Sure, sure. We'll do it. Yes.
Okay. If there is no participants' question, then I think we can wind up. Okay, sir. Thanks. I once again thank you on behalf of organizing committee, and let's wind up. Thank you.
Thank you.
Thank you all. It was nice working with you and hope you learned something new.
Yeah, sure. Thanks.